Good evening and welcome to the live sessions. It is 6 p.m., but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you. Good evening and welcome to week 10 of the live sessions for the NPTEL course on fundamentals of additive manufacturing technologies. This course is taught by Professor Sajan Kapil, who is a member of the faculty of the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. This week we'll be looking at powder feed AM processes. Something we already started last week and got up to a point. I think it was where we were discussing the various types of nozzle designs which may permit a combination of laser and powder interaction. For instance, the laser can come from the center and the powder can come from the sides, either in a continuous coaxial fashion or a discrete coaxial fashion, or the powder feedstock can come from the center and the laser can come from the sides, either again in a continuous or a discrete fashion. And depending on the type of powder feed and laser feed, the type of print that we can get will differ. And we'll spend today's session in understanding how some of the process parameters affect this interaction and what are some of the technologies or existing commercial machines, what sort of build rates they have, as well as some very simple models, a few simple models that try to quantify, say, the bead geometry or the build rates from similar processes. Now, discrete coaxial nozzles that are typically used in powder feed based AM processes use multiple, such as 3 to 4 jets of powder stream, delivering feedstock directly to milk pool via separate and distinct powder delivery channels. The inclination of these channels with respect to each other affects powder flow characteristics and shifts the location of a powder stream's focal point relative to a laser beam, both across and along the plane of deposition. Uh, if this is the plane of deposition, then depending on the inclination of the channels, say the focal point may be directly on this plane, or it may be some distance above, or it may be a defocus beam going some distance below. This is what is meant by uh, change in focal point of the powder stream across the plane of deposition. But what about variations along the plane? In which case, on a single plane, we can have a stream of powder, which is say directly below the deposition head, or based on uh, the variation in powder feed rates or carrier gas feed rates, it can be say we can have a stronger velocity of carrier gas coming from some of the nozzles and a weaker uh, uh, gas exit velocity from the other nozzles, which can tend to shift this focal plane along the plane of deposition. The number of powder streams or channels which participate in this deposition process has significant influence on stream characteristics and also on the catchment efficiency. Catchment efficiency is a parameter which we'll be defining formally in the upcoming slides, but it's an efficiency term. So it will be a ratio of, say, the ideal or total quantity compared to the used or the usable quantity. And in this case, it is physically the ratio of, say, the mass or amount of powder which is actually gets deposited in the form of the bead compared to the total mass or amount of powder which was supplied by us for this reason. See, part of the powder will bounce off the track because of the high velocity of the carrier gas and the high exit velocity the moment it leaves those outlet tubes. Secondly, the laser power may not be sufficient to melt all of the particles, and some of them may remain unmelted and just bounce off or fall to the sides. Or it can also be so that the powder focal spot size is larger than the laser focal spot size, and thus anyway we do not expect all of the powder to be say melted. And the catchment efficiency allows us to quantify the amount of useful powder or the powder which actually went into building up the bead in such cases. And there have been studies which demonstrate that uh, increasing the number of powder channels is not an arbitrary consideration, but with increasing powder channels, the particle velocity in each of the delivery streams will reduce. Uh, this can typically be either because, say, you are still supplying the same volume flow rate of carrier gas, now dividing into more number of nozzles, which of course is expected to lower the particle velocity from each of these streams. But it can also be that because of increasing the number of channels, when they finally come together, the large number of collisions between the powder particles lead to an effective decrease in the uh, particle velocity. And the effect of this reduced particle velocity is an increase in the clad area, which may also be seen to signify a higher catchment efficiency for the same process parameters. Here we have a schematic depiction of a cross section for such a nozzle, where we have these powder delivery tubes coming in from the sides and the laser coming from the center. The powder mass concentration, which is defined as the number of particles per unit area of the focal spot, is negatively correlated to nozzle exit diameter dn and injection radius RAN. So, assuming that this powder mass concentration is denoted by m dot, m dot is negatively correlated or inversely proportional to nozzle exit diameter and inversely or negatively correlated to the injection radius. Injection radius in this case is this quantity depicted here, which is half the nozzle diameter, central nozzle diameter, and dn is the nozzle exit diameter corresponding to these tubes as shown here. Standoff distance is also shown, which is the distance of the nozzle from the focal spot plane. Here, the distance, one end of the nozzle is considered to be, say, intermediate between this inner nozzle section and this outer powder delivery tube. So, somewhere in between. And here we have approximated the powder focal plane. This distance is called the standoff distance. The inclination angle of the powder feed with respect to the vertical is denoted by phi, uh, which is the injection angle. The standoff distance shows a negative correlation with injection angle phi, which again is easy to visualize, because if we keep on increasing this angle, what we can expect is this focal plane to rise up and so the standoff distance to decrease. Whereas for a smaller injection angle, the standoff distance is expected to increase. Standoff distance also shows a negative correlation with nozzle exit diameter. Now, the injection radius is positively related to standoff distance, that is, an increase in Rn increases the standoff distance. And these are some proportionality relations which we can refer to if you are trying to, say, come up with a new design for DED nozzle, or if you are trying to optimize our existing process parameter window, uh, where we need to establish some synergy between the mass flow rate, the uh, say nozzle exit diameter, which will typically be fixed because it is dependent on the tube size and the nozzle size. If you want to vary the standoff distance to, say, defocus or accurately focus the beam. Now, here is another design consideration for discrete coaxial nozzles for powder feed AM processes. which is related to the overlap between the laser spot and the powder spot. Here we have one scenario where we see that each of these, say, large ellipses is the shape of cross section for one powder stream, and here we have four such streams. So let us denote these by the number one. And the reason being that here we have just the powder from one stream. Then we have these other regions where powder from multiple streams are coinciding, which I am hatching in blue, because in each of these regions, what we can see is that the powders from two distinct streams are coinciding. Then we have these small regions, which I am highlighting in black, where there is an overlap of powder streams from uh, three streams at a time. And then there is a central region, which has the overlap of all the four powder streams. The laser spot in this given case is shown by this orange spot right in the center. And what we can see is that uh, it is smaller than, say, region 4, but encompasses region 3 and is much smaller than region 2 and 1. And so there is a lack of omnidirectionality based on if we are going along direction, any of the directions A or the directions B. We can expect different powder deposition characteristics because the powder flow rate or the amount of powder being deposited along that direction is much different. And let us compare it with this uh, second scenario where now the convergence point is larger than the spot dia. In the previous case, it was smaller. Now, what we can see is that there is the overlap of powders from all the four streams in this central region, which is highlighted in green. And the laser spot shown in orange is smaller than this green region. And so, irrespective of whichever direction we move in, whether it is along the four cardinal directions or the other four directions shown by B, we can expect an omnidirectional nature of deposition. Ensuring the overlapping area of overlapping powder streams is more than the laser spot size ensures uniformity of the deposited tracks. This also highlights the importance of achieving correct standoff distance from the substrate, as any change in standoff distance will induce a corresponding change in the overlapping area of the powder streams, which we just encountered in the previous slide. And an improper standoff distance can not only lead to reduced catchment efficiency, that is, you are wasting a lot of powder, but can also affect the track properties, both in terms of, say, the geometry of the deposited track as well as its say, mechanical properties. Um, because of the use of these discrete coaxial nozzles, we have now multiple nozzles through which we can deliver powder, and not all of those nozzles need to deliver the same alloy. As in, we can have different alloys or different metals coming from the different nozzles, which can help us in producing uh, FGMs or functionally graded materials. such as in this case, where you have copper powder coming from nozzles 1 and 2, and tool steel powder coming from nozzles 3 and 4, which lends this reddish or orangish character to say this half of the melt pool, where we are seeing a cross section, and a brownish or dark grayish character to this almost other half of the melt pool, and in between we have a smooth transition zone as shown here. And this will lead, so this is a cross section, and here we have what I presume is a top view, because we what we see is there is this uh, side which is say more orangish or copper rich, and we have this other side which has a say silverish or darkish appearance, which is tool steel rich, and in the center we have a smooth transition. And so there's a direction of gradient uh, across the deposited trunk. The amount of literature on FGMs across the build direction, that is when we are trying to deposit a part, and it will have multiple layers. It is easy to have say different materials across these different layers, because when we are switching from one layer to the next, when the head is lifted and there is no deposition going on, that time can be utilized for say switching the build material or switching the process parameters and so on. However, and so it is such type of FGMs where there is a change in the material itself, or the change in grain size, or change in density or hardness across the build direction, right? Very common. However, the literature on gradation in the deposition plane is very limited. Forced powder streams are part of a discrete coaxial nozzle, with stream 1 and 2 delivering copper to the left side of the pool, and 3 and 4 delivering tool steel to the right. Even though we can expect from the fluid flow and mixing and flow currents inside the molten pool to lend some sort of homogeneity to this powder mixing, but then because of the very steep cooling rates and the high thermal gradients of DAD-like processes, in the solidification time scale, uh, say, or we can say that the system does not really get enough time for these materials to homogenize. The solidification time scale is much smaller than the diffusive time scale, which would have allowed homogenization of these solutes. Again, uh, we must account for and have suitable allowance for nozzle tilt, which is more easily accomplished when we are using discrete coaxial nozzles compared to say one single annular nozzle, uh, because it gives the ability to manipulate carrier flow gas rates for each individual nozzle, and also the flow velocities for individual powder streams. A head tilt of a continuous coaxial nozzle over an angle of 45 degrees renders it non-omnidirectional with increased density of powder on the bottom rather than at the top, simply due to the action of gravitational forces, as shown here, where because of gravity acting downwards, we have a greater density of powders at the bottom and a lower density in this yellow highlighted region. Whereas if we were using or say replacing this single coaxial nozzle by three discrete coaxial nozzles, omnidirectionality even beyond 45 degrees can be easily restored simply by increasing the drag velocity of the carrier gas for the deficient uh, powder stream as compared to the bottom ones. And this will especially be useful for building parts with intricate geometries or overhanging structures, which might require uh, say typically would have required support, but then we have been discussing how for say metal additive manufacturing, typically we want to say avoid the use of supports. So if we are just printing with some simple geometries, it's elementary. But if you are printing some complex geometry or intricate geometry with overhanging structures, we resort to the use of say multi-degree of freedom tables, such as a five-axis CNC table, or multi-degree of freedom deposition head, such as robots. In which case, especially for the case of those robots, the deposition head itself is tilted and may easily exceed angles such as the 45-degree mentioned here. And thus, while printing such structures, if you want to maintain omnidirectionality, it will be very difficult to achieve with just a single coaxial nozzle. Now, what about central feed nozzles, or where the laser is coming from the center and powders are coming from the side? So we are looking at the Lagrangian approach, where we will track the path of one individual particle marked A here. Particle marked A on its path toward the center of the midpool interacts or starts interacting with the laser beam at location X, after which it continues along the indicated direction on its way to the center of the molten pool. Now, from this point X onwards, the particle A strips a portion of the laser beam's energy and directs it towards the center of the melt pool where it is headed. This, combined with the Gaussian heat intensity profile of the laser beam, results in insufficient heating at the edge of the melt pool and excessive heating at the center. One of the factors is, of course, the Gaussian energy distribution, where you have most of the energy concentrated near the center and it decays exponentially as you move away from the center. Second, this particle, which is shown as particle A here, has the longest time of travel because it is covering this longest distance compared to say any other particle over here, which starts interacting with the laser here and covers only a very short distance. Because of the long distance of travel, this particle has ample time to say absorb the energy from the laser, get melted or superheated, and then it deposits all of that thermal energy near the center of the beam. So the laser energy of the laser is already split into two. Some of it is reaching the substrate directly. Some of it is getting distributed to the powder particles. Now, for the fraction of energy which is reaching directly, because of the Gaussian intensity distribution, already you're depositing most of the energy in the center of the cross section. Second, for the portion or the fraction of the energy which got taken up by the incoming powder particles, even those powder particles which absorbed most amount of energy are headed towards the center of the pool anyway. And so the net effect is that you have excess amount of energy in the center and low amount of energy at the edges. And what this leads to is insufficient heating at the edge and excessive heating at the center, which gives us this typical melt pool profile, which will be deep in the center and shallow at the edges. Consequently, the track so generated shows a lack of fusion with the substrate at the edges and excessive dilution at the center. Now, another advantage of using central feed powder delivery nozzle is the minimal divergence of the powder stream. And we have put some numbers to this. So in the case of coaxial nozzles, the recorded efficiency can be as low as only 30%, whereas for central feed nozzles, the efficiency is easily above 80%, which is significantly better. And since we were discussing these laser cross-section profiles, here we have another example for different types of laser beam shaping. We have a ring profile where if you say trace a line along a cross section, you will get these two peaks wherever this line is encountering the ring. Or we have this top hat minus profile, uh, where say, for the sheer reason that it resembles a top hat, because now the intensity is distributed like a hat. We also have a top hat plus, where this intensity at the center is actually added to it. Then we have the Gaussian-like profile, albeit very steep. And depending on these various type of beam profiles, the type of cross section of the bead which you can get are very different. Say for the ring profile, uh, the melt pool is still deepest at the center and narrow at the edges, but the difference in depth is not very high. For top hat minus and top hat plus, we see that the dilation at the center of the melt pool is gradually increasing, whereas the width of the bead is decreasing. And for the Gaussian profile, we see that the depth of the dilution of the melt pool at the center is far larger than at the edges. We can also expect to see some lack of fusion type defects right at the edges, say in these regions, which are now highlighting in red. Besides the use of inert carrier gas for delivery of these powder particles to the deposition region, non-pneumatic nozzles can also be used. The high particle velocity of metal powder delivered using these carrier gases tend to have or tends to lead to a decrease in powder catchment efficiency along with deteriorated surface finish of the deposited clad. The use of conveyance and shield gases further increases convective cooling of the melt pool, thus creating high energy dispersion. Because these gases will typically be fed at a significant volume flow rate. Say numbers like 10 to 30 liters per minute are very common. And because of such high flow, they will also produce convective cooling on the surface of the melt pool. Additionally, this will lead to the generation of surface wave and will significantly disperse the energy which got deposited into the system by the laser. Powder particles traveling with high velocities, upon impacting the free surface of the melt pool, will generate forces of sufficiently high magnitude, and the resulting track often shows very high dilution at the center and lack of fusion at the edges, as we have just been discussing. And studies have also suggested that the entrapment of carrier gas into the melt pool can lead to increased porosity and a decline in mechanical properties of the as-built part. And this is because, as we discussed, I think last week, the solubility of gases in molten metals is much higher than the solubility of gases in solid metal. That is why while the melt pool is okay, while the metals are still molten inside the melt pool, they tend to dissolve or take up gases. However, once the energy source has moved away and the metal starts to solidify, because of the decreasing solubility of this gas in the now solid metal, they are liberated. And these liberated gases tend to stay, if say they are far away from the surface, then they'll tend to get concentrated in small regions known as gas pores. And later these gases can be liberated, leaving behind small, almost perfectly spherical voids. But then again, focusing on the macro picture, these voids will result in part from the use of the carrier gas for delivery of powder particles. Here we also have a very helpful table borrowed from Wang et al., which compares the performance of pneumatic and non-pneumatic powder delivery nozzles. The sample cross-section of non-pneumatic nozzle is, uh, say, remarkably better than that of a gas-assisted bead. The total porosity uh, quantified, say, in a cross-section area is also smaller, and the surface roughness is far better than that obtained by a gas-assisted build process. The mirror finish is around 1 micrometer, and here we can get a surface roughness of close to 2 micrometer, which is, of course, very good. And while non-pneumatic nozzles are not typically encountered in commercial machines, a few such designs have been proposed in the literature, and we will discuss them out of academic curiosity. Most of these non-pneumatic nozzles do not maintain a concentric laser beam, although such a configuration can be devised. In this first example here, where torsional vibration is applied through an offset piezoelectric borrowed from Young et al. Uh, we have this aluminum block and an embedded powder tube, uh, which is made out of glass. The diameter of the tube is between 50 and 125 micrometers. The size distribution of the powder particles themselves is between 3 and 22 micrometers, so very fine powder. And I think the published literature has reports of using pure copper, pure iron, and invar, which is a nickel alloy. The vibration, the frequency of vibration of this torsional vibration using this piezoelectric is 49 kilohertz, and the mass flow rate or the deposition rate is 0.005 to zero point 0.3 milligram per second. That is a very small deposition rate. On the right here, we have another design where we have a powder-filled glass tube vibrated with a ring type piezoelectric instead of an offset piezoelectric like the previous case. And typically, this has been employed for dry powder printing. Here, the diameter of the tube is typically between 110 to 400 micrometers, almost 4 times as large as the previous one. The diameter of the powder particles is also larger, between 14 and 72 micrometers, and a wide assortment of alloys have been printed using this process. While the exact frequency of vibration has not been specified, the mass flow rate, as we can see, is 2 orders of magnitude higher than the maximum in the previous case, going between 10 to 30 milligrams per second. The vibration need not always be, say, transmitted or generated using piezoelectrics alone. It can also be generated using sonotrode and passed on to the powder delivery nozzle using something like a water bath as shown here. And here we have uniform pulsed ultrasonic vibration applied to the capillary tube filled with powder through a water bath. Here the diameter of the tube was 280 micrometers. The diameter of the powder particles was 12 micrometers, so again very fine powder, this time of tungsten carbide. The frequency of vibration was 20 kilohertz and it was not continuous, rather it was applied in a pulsed fashion. And the mass flow rate again being very small of 0.05 milligram per pulse. But then you have 20,000 of these pulses in a second, so it can add up. The vibrations can also be acoustic in nature, that is, they can be generated through sound and transmitted through subwoofers. And on the right here, we have an example of acoustic vibration imparted by subwoofers to the capillary tubes via rigid connections, such as shown here. Here, the diameter of tube is the largest, going as high as 600 micrometers. The diameter of the powder particles is also very large, say between 63 and 212 micrometer. And pure copper as well as S13 tool steel alloy have been printed by this process. The frequency of vibration, because it is audible sound, is far lower. In all previous cases, it was ultrasonic or of the frequency of kilohertz, whereas in this case, it is between 50 to 300 hertz only. And the powder mass flow rate is 5.8 to 35 milligrams per second. Different types of piezoelectrics have also been combined into a single non-pneumatic powder delivery nozzle, such as the combination of a horizontal and vertical piezoelectric on a single mount, as shown here. A surgical hypodermic needle acts as a nozzle in this case. The tube dia is between 200 and 350 micrometers. The powder particle diameter ranges between 10 to 90 micrometers and has been depicted for 316L and soda lime powders. The frequency of vibration is again ultrasonic, and the mass flow rate is 1.25 to 5.8 milligrams per second. Or we can have a concentric laser beam and powder feed, such as shown here in the figure to the right. Uh, I presume there are four powder flow channels. We are seeing one at the back and a cross section of the other two. So, assuming a symmetric distribution, we can expect total four powder flow channels to be there. Here we have a centrally placed piezoelectric which vibrates the flow channel related to the hopper while maintaining a concentric laser beam. The tube diameter in this case is 600 micrometers. Powder particles can vary in size from 45 to 150 micrometers. Materials such as 316L stainless steel and the nickel superalloy Inconel 718 have been printed using this process. The vibration frequency can be as high as 20 kilohertz, and the powder flow rate, again, much higher at 120 milligrams per second or zero point 0.1 gram per second. Now, to summarize all of the different design aspects and how they correlate to the final deposition process for these powder delivery nozzles, uh, some of the important parameters are outlined here. We have the powder injection angle, phi, and as we saw, a lower powder injection angle supports a longer depth of focus, consequently promoting an increased range of passive stability and high deposition efficiency. High mass flow rate is often associated with increased surface roughness and track porosity. The particle velocity uh, can lead to or has an inverse relationship with the catchment efficiency, and lower particle velocities have been reported to increase the catchment efficiency. Reflective materials such as aluminum and copper are difficult to process using conventional IR lasers as compared to shorter wavelength lasers such as blue and green lasers. The melt pool size for conducting materials such as copper is fairly small because of the high thermal conductivity and high thermal diffusivity of the material, and this necessitates using a smaller focal point of powder stream. Coming to the stream characteristics, at the focal spot, powder particle concentration follows a Gaussian trend, which implies the validity of the 1 by E square rule to determine size of the focus spot. Ideally, the spot size of the powder stream should be smaller than melt pool dimensions to ensure high catchment efficiency as we just saw. The primary job of the shielding gas is to prevent melt pool oxidation, and an additional provision of shield gas provides protection for laser optics from metal fumes and powder particles. Uh, the aspect of omnidirectionality is also addressed, where lateral feed nozzles are typically non-omnidirectional and primarily find application only in the sliding of rotary components, whereas coaxial nozzles tend to be omnidirectional and can be employed for part fabrication through additive manufacturing. Uh, there can also be closed loop feedback control of these powder delivery nozzles, and they are called smart powder delivery nozzles with multiple inputs to adjust the feed parameters in accordance with the desired levels of the system in during the print, a form of online monitoring. And especially since the advent of electron beam technology, which requires a vacuum environment, carrier gases cannot always be used for powder feedstock handling. We also saw some of the other advantages of using non-pneumatic powder delivery, such as the better surface roughness, the lower porosity, and the increased, say, bead cross section. And all of these considerations have necessitated the development of gas-free powder delivery nozzles to be used in connection with electron beam as the heat source. Here we have some of the a few popular systems uh, depicted. The first one is the Optomic machines based out of Albuquerque, USA, which have laser power between 400 to 3000 watts, typically using fiber lasers. The melt pool diameter is between 0.3 to 5 mm. The spot size is 0.67 mm. The deposition head consists of continuous discrete nozzle with gas delivery systems and have 40 powder feeders. Deposition rates can be as high as 500 grams per hour, and the system is fitted with either a open or a controlled atmosphere. and you can have both uh, AM and hybrid AM systems. Uh, Machines by DMG Mori are also featured here, which typically have powers between 2500 to 3000 watts using diode lasers. The laser spot diode is between 1.2 to 3.6 mm. The laser head is integrated to the headstock. The deposition head is continuous coaxial in nature. Build rate can be up to 2 kilograms per hour, and argon is used as the carrier gas. The system typically features 5-axis deposition by use of CNC tables. The work volume can be very high, approximately 2.6 meter by 3.8 meter by 2.9 meter, and it is a hybrid system with additive machining stations. We also have this French machine from Beam, which has laser power up to 4000 watts, and two models where the width of the nozzle can vary from zero point 0.8 to 2.4 mm. Build rates can vary between 15 to 130 centimeter cube per hour. The deposition width is between zero point 0.8 to 2.4 mm. Deposition volume can be between 10 to 280 centimeter cube per hour, and power ranges can be between 200 to 2000 watts. The build volume is between uh, is of the order of 400 cross 250 cross 300 to 1200 cross 800 cross 800 mm, and typically comes with a 5-axis machine with seamless controller. Lastly, we have this robotic powder DAD setup, uh, which is from Italy, which uses a 3 kilowatt fiber laser of infrared wavelength of 1070 nanometers. The fiber die itself is 400 micrometer and focal length is 200 mm. Spot die is 1.4 mm. The deposition head features 3-jet powder nozzle from Fraunhofer. The mass flow rate is 9 grams per minute and deposition velocity is 20 mm per second. And Professor Kapil also described this innovative way of developing duct-like or hollow prismatic structures. So I'm not sharing it again. Now we'll discuss some of the other aspects that were presented this week, typically in terms of powder feed and process modeling and its applications. Going back to the roots, powder feed AM essentially derives from laser cladding application where we had a lateral powder feed which was which interacted with a nozzle coming from the central vertically placed and added a layer of material to a substrate, and the intent was to improve the hardness or the wear resistance or corrosion resistance, typically surface properties. And a second improved version of this machine is also shown on the right here, where we have the laser coming from the center, and now the powder, rather than being fed laterally just from one side, was fed say in a continuous coaxial fashion and delivered by powder gas, uh, delivered by the carrier gas. And here we'll formally define the catchment efficiency. The catchment efficiency eta is the ratio of the mass of clad layer to the mass of powder ejected from the nozzle multiplied by 100. For the side feeding nozzle, which was just depicted, the catchment efficiency can be simply calculated by checking two parameters: the size of the molten pool, as only the powder striking in this region will be cladded or melted, and the total amount of powder striking on the substrate. Thus, it can be simplified to the area of the molten pool by the area of the powder striking the substrate into 100. And typically the distribution of powder particles inside this powder beam will be of a Gaussian nature, but if just for simplification we assume a uniform distribution, then the area of powder striking the substrate can be found very easily, as it is the area of the ellipse. with semi-minor axis with minor axis B and major axis C. You know that if the diameter of this beam of particles is dp, its projection on the surface will be dp by cos theta, and so the area of this ellipse will be pi by 4 dp square by cos theta. But what about the size of the melt pool itself? Typically, it is measured by experiment, but for a simplified model, we can lean on the Rosenthal solution for a moving heat source to approximate the size of the melt pool. And here the temperature field is given as T equals T naught plus P naught by 4 pi k e power minus V uh, zeta by 2 alpha e power minus VR by 2 alpha, where T is the temperature field or temperature variable. T naught is the ambient temperature or the preheat temperature. Alpha is the thermal diffusivity, V is the travel speed, zeta is the coordinate system in the moving reference frame given by zeta equals x minus vt, uh, the distance along the traverse direction, and r is the radius of the melt pool. P naught is the absorbed power, and k is the thermal conductivity. This absorptivity for the case of metal is typically say between zero point 0.3 to zero point 0.5, and so only about 30 to 50% of the power which you are supplying to the system is actually getting absorbed by the metal. Also, it will vary as a function of temperature. Now, in the moving coordinate system at zeta equal to 0, meaning at the tip of the beam, the temperature profile will be given as T equals T naught plus P naught by 4 pi k e power minus VR by 2 alpha. Now, we want to obtain the portion of the space where the temperature will be more than melting temperature, solving the equation for T equals T melting. And what this gives us is the region uh, less than R gives a temperature greater than the melting point. We can further use the Taylor expansion for this exponential term, neglecting the higher order terms to get R equals P naught by 4 pi k Tm minus T naught. And again, instead of a Gaussian distribution, if you were to assume a uniform intensity distribution on the beam projected on the surface, this will come to be P naught square by 16 pi k square Tm minus T naught square. And thus the catchment efficiency is obtained as eta equals P naught square cos theta by 4 pi square dp square k square Tm minus T naught square into 100. Let us also quickly look at an example which uses this formula. In a powder feed based AM process, an off-axis nozzle is used to feed material into the molten pool. If with the same setup and laser power, the material is changed from A to B, where the melting point of material A and B are the same, but the thermal conductivity of material B is 4 times higher than the thermal conductivity of material A. Find out the ratio of the catchment efficiencies for both the materials. The formula is already supplied to us. For material A, the catchment efficiency is given as P naught square cos theta, because the angle of attack is the angle of inclination of the powder beam is same, and the power which is applied is also the same by 4 pi square. dp square is also same. It is only the thermal conductivity which is different, so we denote it by Ka square. Em is also the same into 100. Since all of the parameters are the same, what we can say is that eta A is proportional to 1 by Ka square, and eta B is proportional to 1 by Kb square. If we have to find the ratio of eta A by eta B, This simply come out to be Kb square by Ka square. Now the thinner conductivity of material B is 4 times higher. So Kb is equal to 4 times Ka or 16 is to 1, which is also shown here. The same formula has also been used to calculate the catchment efficiency when all of the other parameters are given to us. And for this particular case, where an off-axis nozzle is used to deliver steel metal powder at an angle of 60 degrees from horizontal through a nozzle of diameter 5 mm and a laser power of 1 kilowatt, the catchment efficiency is found out to be approximately 51%. Now, as we have discussed before, the interaction of the stream of metal particles with the laser will be different depending on the region of interaction. And here they have been divided into three regions, 1, 2, and 3. In region 1, the stream of powder particle, if we look at the cross section, will still have an annular shape and will not interact with the laser at all. In region 2, the powder stream would have reached its minimum base radius and it now becomes like a TEM00 profile where you have powder density throughout the section and there is interaction of the laser with it. And in region 3 now, the powder cross section is diverging and the laser cross section continues to converge, and so the interaction decreases. The distribution of powder particles that are delivered from such a nozzle may be assumed to follow a Gaussian distribution in 2D space. In a 2D plane, and as per the rule of Gaussian distribution, the powder stream's spot radius at the focal or convergence plane is determined by the location at which the particle density is 1 by e square of the maximum. Theoretically, we know that for a Gaussian distribution, there is no sharp radius or no sharp boundary at which this distribution will end. However, 95% of all the powder particles or intensity contained within it uh, can be limited to a radius of 1 by e square. And therefore, the particle number concentration at any point xy in the cross section of a slice A given by height A is Na as a function of xy is n naught e power minus r square by k, where k is some constant, n naught will be the peak particle number concentration at the stream center, and assuming that capital R be the boundary radius at which the particle density is 1 by e square of the maximum, we can obtain the constant k equals 2 by r square, which gives us Na as a function of xy equals n naught e power minus 2 square by r square. What about the total number of particles at any such cross section at a given height A? Just like we found the say amount of power contained in a laser beam based on the intensity distribution, similarly we can obtain the number of particles first by finding the number of particles in a strip and then integrating this strip or ring uh, from radius 0 to the radius which we just defined as 1 by e square of the maximum. And this is also shown here, which will give us the maximum number n naught equals 2np by pi r square. And so the powder particle distribution at any height A will equal 2np by pi r square e power minus 2r square by r square. Thus, the particle number concentration at a height in region 2 and 3 can be given by the Gaussian function Na equals 2np by pi r z square e power minus 2r square r z square, or capital R being a function of z, where z is the powder defocusing distance, r of z is the powder flow radius reaching 1 by e square of the peak powder concentration when the powder defocusing distance is z, taking the powder focus point as origin. Now, assuming that the upper surface of the molten pool is a circle, it can be simplified as x square plus y square equals w by 2 square, where w is the width of the bead. As we have discussed, typically your melt pool has an elongated shape. If the center of the laser beam is denoted by this black dot here, then because of the direction of travel, it will have an elongated tail and a smaller head. The primary efficiency of powder can be expressed as the ratio of the quantity of deposited powder to that of the total fed powder. Since only the particles trapped in the pool are deposited, given that the pool surface is assumed here as a circle, the primary efficiency of the powder can then be expressed by the expression given, and it can be seen that the primary efficiency of powder is a function of melt pool radius and powder flow radius. It is dependent on an exponential function involving ratio of the melt pool radius to the powder flow radius. The mass accumulation or mass formation speed M in can be expressed as MP into eta P, or M in equals MP times 1 minus e power minus W square by 2R square. Some particles will bounce out at the molten pool, and let us assume that eta U denotes the powder utilization rate. And so we multiply it to the expression achieved as a correction factor. Typically, whenever we look at the video of a powder DED process, we will see lots of tiny sparks coming out uh, or coming away from the melt pool. And these are nothing but these powder particles which are bouncing off away from the melt pool and not getting deposited. And here, if we assume a parabolic shape of the deposited bead, the bead cross-section profile can also be obtained and the height can be calculated. Thus, the height and width of the molten pool can be appropriately calculated considering the Rosenthal solution for a point or surface heat source. One can also obtain the value of height of the bead and may obtain the width from the above equation. As concerns the optimal step over value, we have already seen how if we want to maintain, say, an almost flat-like surface for two adjacent beads, the area in the overlapping valley, uh, overlapping region should equal the cross-section area of the valley, and this gives us the value of the optimal step over distance as 2/3 of the width of a single bead. Uh, Dilution ratio is also defined in this slide, which is equal to the depth of the melt pool below the surface, assuming the substrate surface as the datum, by the total height of the deposited region, or as shown here, the dilution ratio alpha equals delta by delta plus beta into 100. The optimal value for this dilution uh, for between the first layer and the substrate is between 10 to 30%. If it is far larger than 30%, then the preceding mode of heat transfer can be assumed to be the keyhole mode. Whereas if it is much less than 10%, we can expect to have lack of fusion between this first bead and the substrate. Another quantity which is defined here is the global energy density, or the GED, which is given as the ratio of the input power P to the laser scanning speed Vs and the laser spot diameter dl. The global energy density is used to investigate the interlayer porosity due to lack of fusion in keyhole. The region with low GED are subjected to lack of fusion induced porosity, and the region with high GED increases the chances of keyhole porosity. One of the very important applications of such powder feed DAD processes is for feature addition and the construction of or manufacturing of large scale components. Such powder feed based AM can be used for manufacturing of large scale components such as the Lens 850R system by Optomed, which has an exceptionally large work envelope of 900 cross 1500 cross 900 mm to build or repair large volume components such as blisks, impellers, and shafts. Features can also be added on pre-built parts using powder feed based AM, and other challenges like cladding or feature addition on internal surfaces or difficult to access locations can also be addressed by suitable design of the cladding head. As shown here, where we have a very slim nozzle for easy accessibility and long reach, or we have a specially designed nozzle for cladding and feature addition on the internal cylindrical surfaces. And we again encounter functionally graded materials, which are objects whose properties are designed to vary in different part of the product such that the local properties of the material in a part are suitable for the desired function of the part. It's a biomimetic concept which has been borrowed from nature. Here we have the example of human bone, which is very hard on the outside but soft on the inside. The density varies as a function of distance uh, as we move from uh, say outer to inwards of the bone. And we also have the example of coconut, which is very hard on the outside, soft on the inside, and has water at the center. FGMs based on variable properties can have controlled variation in density or the composition or color, and FGMs based on gradient can have stepwise gradient where say a property can be made to vary. This is location, this is the concerned property, and this variation can be stepwise where we have regions where the property is almost constant and then regions where there is a sudden change in this property, or it can be somewhat continuous or smooth. Now, FGMs are characterized by gradual transitions in either composition or constituent or the microstructure quantified in terms of the grain size, texture, porosity, etc., along at least one direction. It can also happen along multiple directions, and the intended reason for such a controlled variation is to say produce functional changes associated with at least one property. And as we saw before, obtaining such FCMs across the build direction is far more challenging than obtaining FGMs along the build direction. The reason is because across the build direction or in a build plane, we may not always have sufficient time to change the deposition parameters or to change the material of deposition or to ensure that the controlled variation is or the variation is controlled. Say if you want to have a composition variation, we need to ensure that there is proper mixing of the powders on the fly. And again, we have examples of gradient in composition both along the build direction where we are changing the material from SS430 to SS316 and along the build direction where we have multiple powder feeding nozzles. Two of the nozzles on one side feed copper and the other two feed tool steel. Of course, the entire concept has been derived from laser cladding and surface alloying applications, uh, which is a process that attempts to modify the properties of the substrate material using a similar or dissimilar material by melting both in order to obtain a new surface with desired properties, typically associated with corrosion resistance, wear resistance, and hardness. such as on the right here, we have example where the nickel superalloy Inconel 625 has been clad onto a 42 Cr4 MO4 steel, or the drilling head of an oil field has been cladded, presumably to improve abrasion resistance and corrosion resistance and to improve the service life. Or here, where we have change in material from SS304 to SS316L to tungsten carbide. The applications of laser cladding and surface alloying are across shafts, rods, and seals, cylinders and rolls, turbine components, sealing joints and joint surfaces, and for tools, blades, and molds. Another very important application of directed energy deposition processes in general and powder feed based DD processes in particular is that of part restoration. For repairing purpose, a damaged component is digitized and transformed into a mesh representation. This provides the CAD input, which can later be analyzed for extracting the repair volume and tool path planning. The ability to repair the components increases the service life, reduces the cost of operations, and promotes design freedom. On the right here, we have a typical engineering component, a turbine blade, which at the very outset was manufactured from a powder feed based DED process. It got damaged during service, and as we can see, this top part was lost. Now, typically, such a blade would have to be discarded because there were no other means of repairing it, and we would have to build a new uh, blade, even though, say, most of it was still in useful condition. But now, with the advent of powder feed based AM repair, this existing part can be scanned and digitized into a 3D mesh. The region requiring repair can be identified, and material can be deposited very selectively only in that small region to again make this part usable. And, its service life can be extended. Existing parts can also be cladded, just like we saw in the previous case, to improve specific properties such as abrasion or wear resistance. Similar effects can be obtained. Here, the number of layers which were needed were 18. A scan speed of 11.4 millimeters per second was used. The powder flow rate was 22.1 grams per minute, and the laser power was 375 watts. An upcoming application of these powder feed based AM processes is that of the manufacturing of grid stiffened structures. These grid stiffened structures are actually conventional plate and shell members which are further strengthened by repetitive patterns of ribs laid out in a specific geometric configuration as shown here. Grid stiffened structures are popular due to their high load carrying capacity with minimal structural weight, or in other words, because of their high strength to weight ratio. It is a part designed using this paradigm will have very high strength but low weight, and so it is especially useful for aerospace and uh, space applications. Typically, titanium is a material which is well noted for its high strength to weight ratio, but using these defined modifications and the application of grid stiffened structures, even other materials such as say nickel superalloys or even who knows austenitic stainless steels can be rendered with high strength to weight ratios. And these structures typically prevent local flutter, they absorb vibrations, and they possess high bending stiffness. while providing convenient mounting points for other structural members and machine components. To summarize these powder feed based AM processes, they offer several advantages over other AM processes, such as the possibility of high deposition rates to the tune of 3 kg per hour, even though, say, it is actually the wire-based processes which will offer the highest deposition rate, and even among them, wire and arc additive manufacturing is generally regarded as the AM process with the maximum deposition rate. There is a possibility of realizing material-based FGM, and by material-based FGM, what we want to mean is that we can combine various materials or at least two different materials into a single part, either with some stepwise gradient in composition or a continuous gradient in composition using such powder feed based AM process. It has been used and its capability has been demonstrated for the restoration of parts, which helps us in reducing wastage, saving costs, and extending the life of existing parts which may be otherwise minimally damaged through selective repair. It allows for laser cladding, which is the process of improving mostly the surface properties of existing components by either cladding a layer of the same or a dissimilar material, typically dissimilar, with the intent of improving surface properties such as the hardness, the wear resistance, the abrasion resistance, or the corrosion resistance. And it also allows for various in situ processing. For instance, for in situ alloying, where if we have multiple powder nozzles, we can feed different powders from the nozzles, or we can control the flow rate from the different nozzles to combine or alloy these powders on the fly. However, they also come with certain disadvantages. First one being that the support mechanisms typically cannot be incorporated. The reason is not really design based, as in, of course, they can be printed if we use, say, a multi-degree of freedom deposition head that is typically a deposition head mounted to a multi-degree of freedom robot, or if we have a multi-degree of freedom deposition table, which will be an E3-axis or 5-axis CNC table already existing in a CNC machine. Rather, this difficulty arises from the aspect of removal of this support structure. We might print it, but then how do you get rid of it? For very selective or specific combinations such as stainless steel and copper, it can be the support structures made out of copper can be dissolved using concentrated nitric acid, but then it may not be possible for all other combinations of materials. And so the understatement is that support mechanisms are not really feasible using this technology. The layer thickness tends to be high, which is of course expected when we say that we have high deposition rates. But what this also leads to is a loss of resolution. That is, we cannot have, say, very fine features, or we cannot print small objects or small parts, uh, tiny objects or tiny parts, sorry. And because of the very large or high layer thicknesses, the surface finish will be bad. Then, of course, there is the uh, say issue of the low catchment efficiency, where because of the high velocity of the powder as it exits the feeding tubes and the divergence of the powder stream, the amount of powder or the mass of powder which actually goes in to build the deposited bead is only a fraction of the amount or mass of powder which we gave to the system for this purpose. However, irrespective of all these disadvantages, the advantages often trump uh, over other AM technologies. And so, if we want to have repair applications, especially, we will always resort to a powder feed based AM process. Or if we want to have high deposition rates, we prefer these DD like processes. Whereas if we want very fine resolution or very fine features, we'll use a powder bed like process. We'll be talking about powder bed like processes in the upcoming weeks. And after a short break of about 10 minutes, we'll be discussing example problems which will help us in solving the assignments for this week. So let us break for a short while now. Ever. What does it mean? Who?
What do you thought it was?
I thought it meant what? Anything. My wife is like she out of reflex she will say something in Telugu. Even she will say something in Telugu. She'll like Inga ever just carry this. Try to learn. Good evening, and welcome back to the live sessions. Sorry for the slight delay. So the questions we'll be dealing with today, of course, will all concern powder feed based AM processes, and some of them will be on the various relationships and formulae that were derived during the lecture. The present question asks us, in a powder feed based AM process, an off-axis nozzle is used to feed material into the molten pool. If the power of the laser is decreased to half the original power, what will be the corresponding change in the catchment efficiencies? And for this again, we'll refer to the formula relating the catchment efficiency with the various process parameters, which was already derived in class, and we'll just reproduce it here. Yeah, this formula here. So theta is equal to P naught square cos theta by 4 pi square dp square k square Tm minus T naught square into 100. Where of course we already know the meanings of the various symbols. P naught is the laser power absorbed by the material. Uh, Theta is the angle made, I believe, with the vertical by the powder stream. Uh, dp square is the diameter of the powder tube. K is the thermal conductivity. Tm is the melting temperature. T naught is the ambient temperature. And here we are asked to gauge the effect of change in one of these process or material properties uh, on the catchment efficiency. So we are told that the power of the laser beam is decreased to half the original power. So if our case one, then eta 1 is proportional to P naught square, and assuming that everything else remains constant. For the second case, if the power for this is P1, then eta 1 is proportional to P1 square, and similarly eta 2 will be proportional to the absorbed power, in this case P2 square. And we have some relationship between P1 and P2, being that P2 is equal to half P1. What will the corresponding change in efficiency? So it will be best if we find eta 2 by eta 1, because then we can express eta 2 as a function of eta 1. Just okay, which will equal P1 square by P2 square. Of course, assuming that all other process parameters and material properties remain constant, uh, which implies that eta 2 by eta 1 equals P, P1 square by 0.5 P1 whole square, which is equal to 1 by 4. Therefore, the catchment efficiency now is only 1/4 of the original catchment efficiency. The efficiency decreases to 0.25 times the original, and hence option B is the correct option in this case. Question 3 is asking us, in a powder feed based AM process, an off-axis nozzle is used to feed material into the molten pool. If the diameter of the nozzle injecting the powder is 8 mm and the injection angle is 45 degrees, find out the projected area of powder on the horizontal plane. Again, the reason that we are being asked to find the projected area, and this projected area not being, like intuitively equal to the area of the powder stream, is because of the angle of inclination, where the nominal or the diameter of the nominal beam is still the same, but because of the inclination with the vertical, the projected area will be larger and the cross section that we will see will be of an elliptical shape. We are asked to find out the projected area. So if the major axis is A and the minor axis is B, then we know that the area is pi by 4 AB, or pi times the semi-minor axis into the semi-major axis. B in this case is same as dP, which is equal to A at mm, and A will be equal to dP by cos theta, as we already saw during the lecture. This will be 8 pi cos 45 degrees, or pi by 4, and this will come out to be, okay, we can simplify it later. And so the area of the powder cross section will be pi by 4 AB will equal pi by 4 into 8 pi cosine pi by 4 into 8 squared. Cos pi by 4 is 1 by root 2. If you just calculate this quickly, this comes out to be 71.086 square. 71.086. Let's see which is the closest option here. Option B, approximately equal to 71 square. So we are using the same formula, just adapting it as per the scenario posed in the question and obtaining new results. Question 4 is asking us, in a powder feed based EM process, if the power of the laser is decreased to half the original power while increasing the scanning speed to double the original speed, what will be the corresponding change in global energy density? Now, global energy density can be calculated by a straightforward formula that is already separated in the slide. But we should also take a moment to reflect on the physical scenario being discussed here, where we are decreasing the power as well as increasing the scanning speed, which we discussed in one of the previous sessions, would or can be expected to lead to uh, defects such as a lack of fusion, because now the amount of energy which is being input to the material, deposited material, is decreased. We are giving less amount of energy per unit time, or less power, as well as we increase the scanning speed. So the interaction time available to the material to absorb this power or get melted by it is also decreased. Let us now calculate the global energy density, and the formula for GED was already given to us. It is P by Vs by dl. Global energy density GED is the power by the scanning speed into the diameter of the laser spot. We are told that if the power of the laser is decreased to half the original power. So assuming that for the first case, GED1 is simply equal to P1 by Vs1 dl1, and GED2 will be equal to the corresponding power by corresponding scan speed and corresponding laser spot dia. How are they related? Power is decreased to half. So P2 is equal to half P1 and scanning speed is doubled. Vs2 is equal to twice Vs1 while the laser spot size remains unchanged. GED1 is proportional to P1 by Vs1. GED2 is proportional to P2 by Vs2. Their ratio GED1 by just to obtain it the other way. GED2 by GED1 will equal P2 by Vs2 divided by P1 by Vs1 or P2 into Vs1 divided by P1 into Vs2. Now P2 is equal to half P1. We can substitute that here. Vs2 equals twice Vs1. And we can eliminate these parameters. So we have 1 by 4. Therefore, the global energy density now is equal to half of the global energy density originally available to us. And so the GED decreases to 0.25 times the original. Option A is the correct answer. Question 5 is asking us which AM process is the most suitable for repair of damaged components such as shafts and turbine blades. Is it binder jetting, where we have say a reservoir or bed of powder, a thin layer of which is spread out onto the printing region, and then a binder material is selectively dropped in strategic or desirable locations to only locally bind the powder together. An example of such a powder and binder combination can be cement and water. Is it powder bed fusion, where again we have a similar vat of powder, a thin layer of which is spread onto the printing region using a roller or a doctor blade, and then using typically a laser, we melt or in some cases sinter only selective regions of this powder layer to make parts. Is it suitable for repair though? Is it direct energy deposition or is it sheet lamination? Now, we already know that direct energy deposition is suitable because that is something we studied today. But what about these other options? For the example that we saw today, that of a broken turbine blade, imagine a scenario where we have to deposit this missing region using something like a powder bed or binder jetting process. If we were to place this part inside a say vat of powder, exposing only this layer here, which we are now trying to print, and we will have some roller or some doctor's blade trying to spread a layer of powder on top of this. Now that will directly come in contact with this uh, say exposed region of the part and can lead to collision or damage to the roller or doctor blade or damage to the part. So processes such as powder bed fusion or binder jetting, where we must spread a thin layer of powder in each layer, are inherently unsuitable for repair applications. From our discussion on sheet lamination, we already remember how in each pass we have a sheet of material coming in, and getting added to the pre-existing part. It may also be machined, but again, the thickness or the dimensions of the sheet in each case was uniform. It was only later machined to the required specification. So if you try to print this using, say, a sheet-based process, uh, we will have the same width of sheet coming in each layer, and it will again collide with this already existing region. And so none of these other processes are suitable apart from directed energy deposition, a case of which was already illustrated during the lectures. Now, question 6 is asking us that additive manufacturing allows the manufacturing of functionally graded materials or FGMs. Some factors related to the process are listed below. Formation of secondary phases and intermetallics, dilution, that is deviation of actual chemical composition from the design composition, thermal property mismatch, that is a mismatch between the coefficient of thermal expansion and residual stresses. So these are some aspects or some considerations which typically come up in the discussion of say additive manufacturing of FGMs. Now, which of these above factors should be considered while choosing material combinations for FGMs? Is the formation of secondary phases and intermetallics relevant? Whenever we are combining two different metals or two different alloys, we need to look at their phase diagrams to assess if there are any miscibility gaps, whether they are isomorphous, or what sort of phases can form. It is only very rare, such as uh, in nickel copper, where the solubility is complete across all composition ranges. Typically, uh, uh, the formation of secondary phases, which are generally of a deleterious nature, or other undesirable intermetallics, may be expected. And so, when combining or while choosing two different materials to combine into an FGM, of course, we'll be driven by the end application or the end need. But this consideration of the formation of secondary phases has to be taken into account. We discussed how the transition in the desired property, in this case the chemical composition, can either be in the form of, say, if this is in this case composition along the y-axis and location along the x-axis. This transition can either be stepwise, where you have small regions of almost constant property and then sharp jumps across discrete regions, or maybe smooth. In practice, however, even if you want to engineer a stepwise gradient, typically this will never be this sharp. Even if, say, initially it's a very sharp gradient, then there will be like a small dilution region and some sharpness again. The end effect will be that the final variation that we get will be very different from the design intended composition. And so if we are trying to base any properties or desirable features based on just this sharp transition alone, the deviation of actual chemical composition from the design composition has to be taken into account. Of course, just like the metallurgical compatibility, the thermomechanical compatibility also is very important, because if there is large difference in thermal property mismatch, such as, say, for the example of uh, stainless steel with Invar, which is a nickel-based alloy, they may have excellent metallurgical compatibility because iron and nickel tend to have good solubility, but they have very different coefficients of thermal expansion. The For Invar, the coefficient of thermal expansion is of the order of 10 power minus 6, or almost non-existent. And so if these two materials are combined into an FGM, we can expect that there will be large thermal property mismatch across the dissimilar interfaces, which can lead to the uh, which can lead to defects, and also the generation of residual stresses, which, as we have been discussing, are unavoidable and are can be very dangerous, especially if they are of the tensile kind, which will lead to the opening up and propagation of existing cracks. And thus, all of the considerations listed above must be taken into account when choosing candidate materials for combining into an FGM. Question 7 is asking us, for powder-based AM processes, which technique of powder processing produces the finest quality powders in terms of morphology and quality? Even though this is not something which was discussed in the lectures, we just take a minute to discuss the aspects of the powders generated by these various techniques. Typically, we just take the powder feedstock as an input quantity, which we do not really control and just buy from the manufacturer. But knowing the various types of manufacturing methods can allow us to exercise finer control over its features. Typically, the metal feedstock will be melted and then it will be atomized into small particles, which then solidify and form the characteristic powder. This atomization can be done by water, in which case the produced particles are typically of irregular shape, not always spherical, and so the sphericity is poor. Or this atomization or breakup of the molten metal into these small droplets can be done through the use of some inert gas like nitrogen or argon, in which case the powders will have comparatively better sphericity, though still not perfect, but they will be plagued with gas porosities because of the uptake of this gas. Or the state of the art process, which is plasma atomization, where the powders have almost perfect sphericity and regular shape and also do not suffer from gas porosity. And so the finest quality powders in terms of morphology and quality are produced by plasma atomization. Question 8 is asking us, a functionally graded material or FGM can have variation in which of the following properties? Is it in terms of density, an example of which is the human bone? Is it in terms of chemical composition, which is from the example we were discussing just previously? Or is it in terms of color? Or can all of the above be engineered into an FGM? Chemical composition we already saw in I think one of the previous questions, and also in the slides where we had the example of copper being combined with tool steel into a single part. Similarly, the density can also be varied, and based on the control of process parameters, we can engineer highly dense and somewhat porous regions into a single part. And as we have seen towards the beginning of these sessions, when we were being introduced to the various AM technologies, we saw examples of parts which had different colors throughout their body. And these colors were not just on the surface, but all the way through, as in the very material used to make the part had a different color. And so all of these above can be carefully controlled and engineered into a functionally graded material using additive manufacturing technologies. And I see that we have exceeded the time for our session. I thank you all for tuning in to week 10 of the live sessions for the NPTEL course on fundamentals of additive manufacturing technologies. I am Sourav Goswami from IIT Bombay, and I hope to see you all next week. Thank you very much.